We have a program for the third level course, Understanding Space and Time. It deals with the equivalence of mass and energy and some of the other revolutionary consequences of special relativity.
We know that the absolute time of Newton has been displaced by the relativity of time. Physical processes take place more slowly when the system being observed is in relative motion. Moving clocks beat more slowly. Let's see where this leads us. We'll start with the light clock, which works by bouncing light pulses between reflecting walls. When the clock is stationary, a pulse of light moves back and forth in a certain time. But when the clock is set in motion with speed v, the light traverses a longer path and takes a longer time for one tick, one period of the clock. The increase in time is given by the factor gamma. Now we're going to use these same reflecting walls to draw some other interesting consequences of special relativity. This time we take two vertical walls and we imagine a light source sending out pulses from the center toward the walls. Since they have equal distances to travel, the pulses reach the walls at the same time and return to the center also at the same time. Now let's imagine a similar setup as a kind of signaling system inside a spaceship so that the light reaching the walls this time is picked up. A large space station is nearby observing everything. Relative to the observing station, the signaling spaceship is in uniform motion. How will the light pulses be observed to travel? Now the left wall advances to meet the light pulse, while the right wall retreats. So to the observer in constant motion relative to the spacecraft, the consequence of light traveling at its invariable speed is that the two light pulses hit their respective walls at different times, the left-hand event here occurring earlier. If the spaceship were moving in the opposite direction, it would of course be the right-hand pulse that would arrive first. But notice, as before, that the light pulses always travel at constant speed c. Depending upon the relative motion of the observer, then, these events occur at the same time or at different times in either order. All right, but now let's change the signaling system. Let mirrors be installed at the ends of the ship so that the light pulses are reflected back to the center of the spacecraft. How will this new signaling system operate when observed from the passing space station? So the time situation will be reversed on the return trip, and the two light pulses return to the center at the same time, simultaneously. Simultaneous events at the same point in space are simultaneous for all observers in uniform relative motion. But two events at different spatial points that are simultaneous for one observer are not simultaneous for another observer in constant relative motion. Does that mean that a simple act like this could appear to another observer as the ball landing in my hand before I drop it? No. The reason is that there is a physical object in motion throughout this act, and any observer at whatever relative speed will be able to follow it and has no choice but to agree on the same sequence of cause and effect. This situation did not apply in the case of the spaceship, as the two light pulses had no cause and effect relation. The absoluteness of the speed of light, in the sense that no material object can ever attain it, was fundamental to the conclusions we have just drawn. But one thing we have not asked is this: what mechanical property prevents that limit from being attained? What is it in the nature of matter that makes the speed of light inaccessible? One way to investigate this question is with atomic particles, and in doing so, we shall be led on to further implications of special relativity.
When protons are channeled down long vacuum chambers, very fine beams can be produced, and these can be manipulated with very great accuracy. Inside particle accelerators, like this one at the European Nuclear Research Organization near Geneva, bunches of protons are driven up to very great speeds by electric fields. These are cleverly timed to keep urging the protons ever faster. This proton synchrotron, as it's called, was built in the shape of a ring, about 200 meters across. It produces protons traveling within a fraction of a percent of the velocity of light. In 1976, the protons from this ring were injected for the first time into a giant new ring of magnets many times larger than the proton synchrotron. Buried beneath the soil, this super proton synchrotron measures more than 2 kilometers across and is one of the most powerful machines ever made. Once inside the SPS, the protons are again subjected to strong electric fields. These urge the protons on, so that eventually they end up with 40 times more energy than when they entered. But remember, the protons started in the SPS at almost the speed of light. So what happens to their speed as the energy goes up? Well, there's the energy going up. It goes up from 10 GeV up to 400, which was the factor of 40. But look at the velocity. It goes up in the first phase of the acceleration quite quickly to almost the speed of light, but then it just flattens off. How can we explain that? How can you push something along so that it gets more and more energy, but it doesn't go any faster? Well, it must mean that the inertia of that particle is going up, its inertial mass. And we can show that, too, on this output. There in the center of the screen, you've now got the mass displayed. As you see, it's going up along with the energy. And that has to be the explanation of why it is that you can't push a proton or any other particle faster than the speed of light.